Hello students, in the previous video we have learnt a hybridization of elements involving s and p orbitals and the typical examples we have learnt are sp hybridization, sp2 hybridization and sp3 hybridization. And in today's class we are going to learn hybridization of elements involving d orbitals. And we are having here 4 points. Let us discuss one by one, right? The first point, if you see, the elements present in the third period contain d orbitals in addition to s and p orbitals, right? The first point is that the elements present in the third period of the periodic table which has been proposed by Mendeleev, in the third period it contains d orbitals along with the s orbital and p orbital, right? The second point is the energy of the 3d orbitals are comparable to that of the energy of 3s and 3p orbitals. This point is very important, students. Keep in mind what is that the energy of 3d orbitals are comparable with that of 3s and 3p orbitals, right? And at the same time the energy of 3d orbitals are also comparable with those of 4s and 4p orbitals. What is the point? That the energy of 3d orbitals is also comparable with that of 4s and 4p orbitals. Now if you see the third point, okay, you can now get to an analysis that as a consequence of hybridization, what is the meaning of hybridization? Mixing up of two or more atomic orbitals of slightly different energy to give new orbitals of equivalent energy. The phenomena is called as hybridization, and the new orbitals obtained are called as hybrid orbitals, right? Now it reveals that if a 3d, 3s and 3p, if the energy of these three orbitals is comparable, then it reveals that there is a possible of a hybridization of 3s orbital, 3d orbital and 3p orbital. Similarly, if a 3d orbital is going to mix with that of 4s and that of 4p, then again we can say that hybridization is possible among these, that is d, s and that of what p is possible. But the fourth point is a very important point. What is that fourth point? Since the difference in the energies, what is this? Since the difference in the energies of 3p and that of what 4s orbitals is significant. What does this mean? It means that here the principal quantum number is 3 and here the principal quantum number is 4, isn't it? So there is a difference in the energy. And if you see the n plus l value, so if I take here 3p, for 3p n is equal to 3 and for p orbital the l value is 1, so 3 plus 1 that will be what 4. And if I take a 4s orbital and if I go for n plus l value, n for 4s is what 4 and here I'm sorry, so for yes it is, okay, for yes, okay, the value of l will be what 0, so 4 plus 0 is equal to what 4. Of course both are having what the value 4, but this comes with respect to 3 and this comes with respect to what 4, that is principal quantum number. As a result no hybridization involving 3p, 3d and 4s orbitals is possible. This point is very important, student. What is that? There won't be hybridization involving 3p, 3d and 4s orbitals is not possible. Now let us take the example of PCl5. So PCl5 is nothing but called as phosphorus phosphorus pentachloride. What is that? PCl5, right? And the hybridization in PCl5 is sp3d hybridization. Okay, the central element is phosphorus, whose atomic number is what? 15. Whose atomic number is 15. And if I write the electronic configuration, you can see that 1s2, 2s2, then followed by 2p6, then 3s2, then followed by 3p3. Okay, phosphorus is belonging to what? A 15th group, that is with respect to nitrogen. So therefore it is called as what? The family member of what? Nitrogen. As nitrogen is half filled, so the group elements are also what? Half filled. Why? Because p orbital capacity is 6, but here you can see only 3 are present, so therefore half filled, right? Now the ground state and excited state of a phosphorus has been mentioned. So if you see the ground state, here it is, and this is the excited state, right? Now what about this 3s and 3p? So this 3s2 and 3p3, this is called as valence shell, right? Now in 3s there are 2 electrons, you can see here. In 3s there are 2 electrons, and in 3p there are what? 3 electrons. This is ground state. During excited state, now when it is present in excited state, during hybridization, energy is what? Exchanged between this phosphorus and the orbitals of what? Cl. So at that time phosphorus gets excited, where one of the electron from the 3s orbital is present in what? 3d. Now this is what? 3d orbital here. So one of the electron from 3s orbital will be present in what? 3d orbital. Now if you see how many orbitals are having unpaired electron, this is 1, that is a 3s, and this is what? 3p. All are having what? 1 unpaired electron, and this is one more orbital, that is what? 3d orbital, right? As we have already learnt in the previous slide, the energies of 3s, 3p and 3d are comparable. For that is the reason during excitation one of the electron from 3s orbital will be present in what? 3d orbital. Now totally how many s? 1 s will be there. How many p? 3p will be there. How many d? 1 d will be there. What is the hybridization of each orbital? Each orbital will be of sp3d hybridization, right? Each orbital will be of sp3d hybridization. How many will be there? That becomes important. 5 will be there. Okay, now these 5 sp3d orbitals will be overlapped with one of the 2pz orbital of a chlorine atom. So you can see that this is one chlorine, this is another chlorine, third chlorine, fourth chlorine and fifth chlorine. All these 5 chlorine atoms will be giving 1 electron to that of the phosphorus atom, where you can see here 2 electrons are present. That involves in what? Bonding. Similarly, this will be the second bond, this will be the third bond, this will be the fourth bond, and this will be the fifth bond, right? So you can see sp3d hybrid orbitals are filled by electron pairs donated by 5 Cl atoms. Now the 5 orbitals, which are those 5? 1s, 3p and 1d orbitals are available for hybridization to yield a set of 5 sp3d hybrid orbitals, which are directed towards the 5 corners of a trigonal bipyramidal as depicted in the sense what? You can see this diagram here, right? So here what you can see, phosphorus is present at the center, and this is the water trigonal, okay, or we can call it as water triangular in shape, okay, where you can see 3 chlorine atoms are present at the corners of triangle and the remaining 2 are present above and below. Such a shape is nothing but called as trigonal bipyramidal. Such a shape is nothing but called as trigonal bipyramidal. So this structure, if you see here, it is drawn in this manner. So this is the triangular here, phosphorus present at the center, here one chlorine atom, here another chlorine atom, here the third chlorine atom, above one more will be there, and below one chlorine atom will be there. And if at all if you join this, then you will be having water trigonal bipyramidal structure. Now it should be noted that all the bond angles in a trigonal bipyramidal geometry are not equivalent. It means that all the 5 phosphorus Cl bonds are not same. In PCl5, the 5 sp3d orbitals of phosphorus overlap with the singly occupied p orbitals of chlorine, which is that p orbital that will be water 2p z orbital of chlorine atom to form 5 phosphorus sigma bonds, Now the 3 phosphorus chlorine bond lie in one plane, which is that plane. So this is the plane here, you can see this is the plane, okay, will lie in one plane, making an angle of 120 with each other. So this is the angle which is called as what, 120 between the chlorine atoms which are present in one plane. So these bonds are termed as equatorial bonds. I will be showing the diagrammatic representation here. Phosphorus, this is one chlorine, this is another chlorine, and this is the third chlorine, which are present in water one plane, okay, and here the bond angle is 120 degrees, okay. And these 3 bonds, this is first bond, this is second bond, and this is third bond, which are called as equatorial bonds. These are called as equatorial bonds. The remaining 2 phosphorus and Cl bonds lie, one will be present above and the other will be lying water below the equatorial plane. So this is the 4th Cl here and this is the 5th Cl here. So the shape becomes water trigonal bipyramidal, where the angle will be water 90 degree, which is that angle. So this angle will be water 90 degree with the plane, right? And these bonds are called as axial bond. So this bond is called as axial bond. Again, this bond is called as axial bond. As the axial bond pairs, now see this, as the axial bond pair. So here we are having this bond, the electron present in this bond are called as bond pair, right? So therefore axial bond pair suffer more repulsive interaction from the equatorial bond pairs. It means that this bond and the equatorial bond will be having interaction, due to which axial bonds have been found to be slightly longer. This point you have to remember. Equatorial bonds are shorter, but whereas the axial bonds will be slightly longer and hence slightly weaker. One should remember that bond length is inversely proportional to bond strength. As the bond length increases, bond strength goes on decreases. For that is the reason we say that the axial bonds are slightly weaker than the equatorial bonds, which makes PCl5 phosphorus pentachloride molecule more reactive in nature. I hope you understood the hybridization of sp3, the angle, the equatorial bonds, the axial bonds, and the axial bonds are longer in nature. If bond length is larger, bond strength is weaker, and this is what makes PCl5 more reactive in nature. Now let us concentrate on the another example, that is a formation of a SF6, that is sulfur and fluorine. And fluorine, how many are here? That is 6 fluorine atoms are here, right? And the hybridization is sp3d2. So far we have learned sp3d, but now we are going to learn sp3d2 hybridization, right? And we know that the sulfur in the ground state, okay, sulfur, this is the atom which is present just below the oxygen, whose atomic number is 16. And if it is a 16, I can write the electronic configuration as 1s2, 2s2, 2p6, 3s2, then followed by 3p4. So this is the outermost valency shell, that is 3s2 and what, 3p4, right? So if you see in the ground state, the valence shell has been mentioned as a 3s2 and 3p4. so here you're having what, 2 electrons, and here you're having what, 4 electrons. Is it clear now? So during excitation, this was all with respect to ground state. When it is present in excited state, we have one concept you have to understand, students, right? What is that concept is, so here directly it has been mentioned as excited state, but during excitation again there are first excitation state and a second excitation state. Why? Because in the case of d orbitals, you can see in the ground state no electrons are present, but in the case of excited state there are 2 electrons present. It means sulfur in its second excitation state only we can achieve 3d with the 2 electrons, right? In the first excited state, one of the electron from 3s orbital will be present in 3d, and in the second excitation state, one of the electron from 3p orbital will be present in what, 3d orbital. As a result, we will be getting now totally 6 orbitals. Which are those? One will be 3s, remaining 3 are what, 3p, and the remaining 2 are what, 3d. Totally how many orbitals will be there? 6 orbitals will be there. These will undergo hybridization. Which type of hybridization? That is sp3d2. Each of the sp3d2 hybrid orbitals will overlap with each of what, 6 fluorine atom. Can you see? This is first fluorine, second fluorine, third, fourth, fifth and 6th, to form 6 SF bond. How many will be there? 6 sulfur fluorine sigma bonds will be there. Thus we can say that the sulfur atom in SF6 is sp3d2 hybridization. Is it clear, students? Now you can see that in the excited state, the available 6 orbitals, which are those 1s, 3p and 2d, are singly occupied by electron, or we can say unpaired electron. These orbitals hybridize to form 6 new sp3d2 hybrid orbitals, and which are projected or directed towards the 6 corners of a regular octahedron. This we are going to study in the next slide. Okay, in the of a corner, sorry, 6 corners of a regular octahedron in SF6. These 6 sp3d2 hybrid orbitals overlap with singly occupied orbitals of fluorine atoms to form 6 SF sigma bonds. Thus SF6 molecule has a regular octahedral geometry. What is that? Octahedral geometry. Now you can see in this diagram, many typical diagrams are here. Okay, now if you see this first one, okay, this is nothing but called as what? Octahedral geometry. Central atom, that is what, sulfur is present. This is first bond, this is second bond, this is third bond, this is fourth bond, this is fifth bond, and this is a sixth bond. Here a fluorine atom, here fluorine atom, here fluorine, here also fluorine, here also fluorine, and here also fluorine. This is the structure of this molecule. If you see orbital diagram, so this is one orbital, which is that sp3d2. This is the second one, this is the third one, this is the fourth one, fifth one, and sixth one. Is it clear, students? So electron pair geometry, if you see here, central atom is what? Sulfur. One bond with what? Fluorine here. But if you see fluorine, atomic number is what? 9. And if you see electronic configuration, 1s2, 2s2, and then followed by 2p5. Is it clear now? In order to become stable, it shares one of the electron with the combining atom. At that time it becomes what? 2p6, right? And the remaining electrons will be present in case of fluorine outermost shell. How many will be there? 3 lone pairs will be there. For that is the reason here you can see here one fluorine atom which is having what? 3 lone pair, which have been mentioned as what? First dot, second dot, third dot, fourth dot, fifth, and what? Sixth. So each fluorine atom will be having what? 3 lone pairs. Okay, and if you see the bond angle, here, the bond angle between the axial bond and that of the equatorial bond is 90 degree, and between any of these equatorial bonds, again it will be 90 degree. And what is the molecular geometry? Molecular geometry is octahedral. Molecular geometry is octahedral. I hope you are able to see this. Now sulfur is here, this is 1 fluorine, this is 2nd fluorine, this is 3rd fluorine, this is 4th fluorine, this is 5th one, and this is 6th one. Now join this. Okay, now this we have to join it in this manner, and the next you have to join this and this as well as this, and again you have to join this and this, again this and this. Altogether it becomes octahedral geometry. 6 sp3d2 hybrid orbitals overlap with singly occupied orbitals of fluorine atoms to form 6 sf sigma bonds. Thus sf6 molecule has a regular octahedral geometry. I hope you understood, students. Now let us have some competitive questions which has been already sent to you in the form of PDF file. That only we are going to discuss now. Later we'll be giving some assignment along with theory questions, right? Now the first question, the valence bond theory explains shape, the formation and directional properties of polyatomic, not diatomic, polyatomic molecules like methane, ammonia and water in terms of. Now you have to find out the correct option. Now let us go with respect to that methane and NH3 and H2O. This carbon central atom, nitrogen central atom, oxygen central atom, all are having which type of hybridization? Sp3. All are having Sp3 means atomic orbitals are undergoing hybridization, isn't it? So if carbon was there, okay, it was tetrahedral, okay, tetrahedral Sp3, 4 Sp3 hybrid orbitals are directed towards the 4 corners of a tetrahedron. Then each of this is going to overlap with the hydrogen, isn't it? First what was formed? Hybridization was formed. So that answer is here, hybridization of atomic orbitals. After hybridization, what formed? Overlapping. Each of the sp3 hybrid orbital overlapped with 1s1 orbital of hydrogen, isn't it? So that is here overlapping of atomic orbitals. So therefore we can say the correct option is option C, that is both A and B. And the same will be happening with respect to nitrogen here. Even nitrogen is also sp3 hybridized orbital. How many will be there? 4 will be there. In that 4, one will be having a lone pair and the remaining will be present here, and each of this will be overlapping with the hydrogen here. Now this is nothing but called as pyramidal in nature. So this was a tetrahedral methane, but in case of ammonia, presence of one lone pair makes the molecule undergo distortion and the shape of the molecule is pyramidal in nature. And if you see that with respect to water, there are 2 lone pair of electrons, because of which the angle will be reduced from 109.5 degrees to 104.5 degrees. As a result, the shape of the molecule becomes bent or angular or V-shaped. Now second question, VBT theory is based on, VBT theory, that is valence bond theory, is based on, okay, if you see it is a theoretical question, and I would like to suggest that VBT theory is based on knowledge of atomic orbitals and electronic configuration of elements, overlapping criteria and the hybridization of atomic orbitals. Apart from that, it is also based on principle of variation and superimposition. So therefore the correct option is option D, that is all of the above. Next question, the below potential energy curve is given for the formation of hydrogen molecule as a function of internuclear distance of hydrogen atoms. At what point in the curve hydrogen is found to be the most stablest state, right? Now if you see, this is x-axis, this is x-axis, and if you see here, this is y-axis. At y-axis there is energy which is expressed in terms of kilojoule per mole, and along x-axis it is nothing but internuclear distance, okay? And if you see these 2 dots which are nothing but hydrogen, okay, this is nothing but 2 hydrogen atoms, that is distance of separation. It means they are far from each other, okay, and that is called as point D. At point D, when the 2 hydrogen atoms are formed, then there is no formation of hydrogen molecule, right? So if they move in this direction, then they are coming closer to each other. During coming closer to each other means overlapping is possible. Okay, at a certain point they will overlap in such a manner such that this is nothing but called as what? A bond energy. Okay, this is nothing but called as what? A bond energy. It means that at point C molecule is formed. At point C molecule is formed, and this is nothing but called as what? A bond length. This part, okay, is nothing but called as bond length, and this is the energy that is called as what? A bond energy. It means it is less than 0. It means energy is what? Liberated during what? A bond formation. Now suppose if they cross this line also, then what happens? Overlapping becomes more. At that time molecule becomes unstable and the curve reaches above here. At that time it is highly unstable. So therefore in order to form a bond, energy has to be liberated, and which is that point? That is nothing but called as what? A point C, right? And they have asked us at what point in the curve hydrogen is found to be most stable, and that point is nothing what? A point C, and the option is what? Option C here. Is it clear now? And if you see here how much is the energy liberated, that is 435.8 kilojoules per mole, right? And the same question is extrapolated in the next question, that is how much energy is required to dissociate one molecule of water? Hydrogen molecule. For formation of hydrogen molecule we require the energy liberated is how much? Minus 435.8 kilojoule per mole. This much is the energy liberated during the formation of 1 mole of water? Hydrogen. Okay, and in order to break that hydrogen molecule, because here the question is dissociate, so therefore the same energy, but that will be in terms of positive, because energy is needed or energy is what? Required. At that time this much energy, that is we have to supply 435.8 kilojoules per mole. That is the energy required to dissociate one molecule of hydrogen molecule. Okay, then we'll move to the next question, the fifth question. Okay, the formation of hydrogen molecule takes place. The formation of hydrogen molecule takes place when it is forming? When the first option, the energy state is minimum. That is very much important. When the energy state is minimum, then only hydrogen molecule is what? Formed. Second important point is that what? When energy state is minimum, orbital must have been undergoing what? Overlapping. So therefore the two hydrogen atomic orbitals must be undergoing overlapping to a larger extent, right? So therefore the correct option is option C, that is formation of hydrogen molecule takes place when both A and B are happening. That is energy state should be minimum and the atomic orbitals must be undergoing overlapping to a larger extent. Now sixth question, if you see, the molecule of hydrogen atom is formed due to the overlapping of orbitals of two hydrogen atoms. This is sure. Which of the following types of overlapping takes place in the formation of hydrogen molecule? One has to remember that for hydrogen there is only one electron, and that one electron is present in s orbital. S orbital is what? A spherical in a nature, and if you see the axis over there, this is x axis, this is y axis, and this is what? Z axis. Okay, so there is a spherical in nature, so in all the directions it is the same. So altogether we require is what? Two s orbitals, and they should approach in such a way such that the electron density with what? Positive. Okay, now this positive is nothing but it is not called as charge. It simply reveals us that what? The electron density is present in one particular side. When they overlap, both should be what? Coming closer to each other, and that is possible only in the case of option A. You can see that this is one orbital of hydrogen, this is another orbital of what? Hydrogen with the positive sign. That is nothing but electron density. When overlapping is taking place, bond is formed. When bond is formed, energy is liberated. When energy is liberated, molecules becomes what? Much more stable, right? Now if you see the seventh question, when the orbitals of two atoms, okay, when the orbitals of two atoms, if they come close to form a bond, then absolutely one can say that there is what? Overlapping, right? and if that overlapping, if at all, it can be positive or it can be negative or zero depending upon the sign. I hope you understood this. That is nothing but called as a phase. Okay, if at all, if it is, now this is p orbital. Okay, this is p orbital, and here we are having positive and here we are negative. Now this doesn't mean that electron is present here, electron density is present here. Okay, that is called as what? Positive. And if s orbital is there, and if it approaches in this direction, and if it approaches in this direction, then bond is formed. But if it is approaching in this direction, it is called as what? A zero overlap. Is it clear? So therefore, depending on the sign phase, okay, and the direction of orientation of the amplitude of the orbital wave function in space, that is important criteria. Okay, now the condition for positive overlap. What is the condition of positive overlap? First thing is that orbitals forming bond should have what? Same sign, isn't it? Orbitals forming a bond should have same sign. That is nothing but called as phase, and that phase is nothing but what? Electron density. And whenever they are having same sign or phase, orientation is important in space. Just now I told you, okay, if a p orbital is here and if another p orbital is coming in this direction, the orientation is the same, and this is the electron density here and this is the electron density here, then only orbitals overlapping is possible, isn't it? Now which is this? Now if at all, if this p and if this p along what? A pz axis, right? And if I take x, then this is called as what? A p along x axis, and this is p along x axis. When they approach each other, that is what? Positive and positive. And here if I say negative and negative, so this is the same sign, and this also is called as what? Same sign. When they come nearer to each other, sideways overlapping is possible. So this is a sideways overlapping is possible. So here electron density will be more, bond is formed, which is that bond, pi bond, because this is a p bond, a lateral overlapping, or simply called as what? A sideways overlapping, right? At the same time, I say that the orientation is important. So from this explanation we can say that orbitals forming bond should have same sign, that is called as phase, and orientation in space. So therefore the correct option is what? Option A. And now we'll move to the next question. And the next question, which of the following does not represent a positive overlap? So the question is, does not represent a positive overlap. Let us see the option. So if you see the option, so these are px orbital. Okay, so px orbital are like this, right? So this is in what? X axis, and their lobes you can see both are having what? Positive. That is nothing but same sign. So therefore if they overlap laterally in this manner, then a bond is formed, and that bond is nothing but called as what? A pi bond. So this is what? A correct positive overlap, but they are asking which does not. Okay, so leave this. Second one, option B, if you say here it is along what? A z axis, it means p orbital which is present along z axis. Okay, and this is the p along z axis, this is another p along what? A z axis. And if you see here, this lobe is carrying what? A positive sign, and this lobe is carrying what? A negative sign. So this is called as what? A negative overlap. So therefore this does not represent what? A positive overlap. So the correct option is what? Option B. Okay, and if you see that of C, a pz orbital, that is nothing but a p orbital which is present along z axis, it is overlapping with what? S orbital. Let it be. So therefore p and s, so it is nothing but formation of overlap between p orbital and that of s orbital. Both are having what? A same sign, that is called as in phase. So this is possible, but they are asking what? Not possible. So option is what? Option B. And similarly the same, that is with respect to D. So both are having what? Same sign, so it is positive overlap. And now we'll move to the next question, question number 9. Okay, sigma bond is more stronger than pi bond. Okay, absolutely it is correct, because sigma bond is always stronger when compared with what? A pi bond. The reason is, in case of sigma bond, a head-on overlap will be what? Possible, and in case of pi bond, a lateral overlap is possible. Now the question is, the sigma bond is more stronger than that of pi bond because, now you see the first option, large extent of overlapping in pi bond. No, if it is large overlapping in pi bond, then it reveals that pi bond is stronger than sigma bond. So this option is not correct. Go to the next option, small extent of overlapping in what? Sigma bond. No, even this also is not correct. Why? Because large extent of overlapping in sigma bond makes what? Sigma bond stronger. So therefore this is not correct. Next, go for the next option, small extent of overlapping in the case of what? A pi pi bond. So this is the correct option. What is that? Extent of overlapping in pi bond is a small, okay, and we know that it is always a small. For that is the reason, if a small extent of overlapping in pi bond is there, then it is what a weak bond. It absolutely means that sigma bond is what a stronger bond. Is it clear now? Now let's go to the next question. According to Pauling, the atomic orbitals combine to form a new set of equivalent atomic orbitals. Okay, atomic orbitals combine. Why do they combine? In order to form a molecule. What happens? Hybridization takes place to give what? A new set of equivalent atomic orbitals, which are nothing but called as what? A hybrid orbitals, right? Now this is question number 10. Make sure that this is question number 10, okay, and the next question will be question number 11 here. So this is question number 11. Which of the following is not an essential condition for hybridization, right? Okay, if you see the option, whenever hybridization takes place, the shell that is involved in hybridization is always what? A valence shell. So first option is correct, but they are asking which is not. Okay, so leave it. The orbitals undergoing hybridization should almost have equal energy. That is 100% true only. Whenever orbitals are undergoing hybridization, they should be having almost what? A less energy difference, or almost what? A equal energy, right? And the third option, promotion of an electron is an essential condition prior to what? A hybridization. So this is not an essential condition. Why? Because if you take beryllium, right, its atomic number is what? A 4, and this is 1s2 and then followed by 2s2. But beryllium belongs to s block, group 2 element. Only valence is what? 2. That combining capacity of an atom of an element is called as a valency, and beryllium is a divalent species. And if you see here, this is what? 2s2. So here you can see that. So here you can see that 2 electrons are there, okay, and if at all, if beryllium forms what? The compound BeCl2, there is no need, that is promotion of an electron is not an essential condition prior to what? A hybridization. So this s orbital will combine with the p orbital of what? Chlorine to form a sp hybridization, and we already know that if it is sp, the bond angle is what? 180 degree, and the molecule becomes what? A linear in nature. Central atom is beryllium, here 1 Cl and here 1 Cl. The bond angle is what? 180 degrees. So what is the correct option? Correct option is what? C. Promotion of an electron is essential condition prior to hybridization. That is the what? Option, but that is not the correct one. Which of the following is not an essential condition for what? Hybridization, they have asked. Is it clear? So the 11th question has been completed. Now we are going to the 12th question here, right? Mixing up of s, which is that s, 1 s and 1 p orbital, okay, 1 s and 1 p orbital, resulting in the formation of what? 2 equivalent sp hybrid orbital, or we can say that what? It is undergoing sp hybridization. Which of the following orbitals are used for sp hybridization by convention? Okay, now here we are having p orbitals, okay, so one is px, other one is py, and other one is what? Pz. By convention, whenever p orbital is involving in sigma bonding, remember during sigma bonding it is always what? Pz orbital, right? So 1s and 1p, which is this p, that is what? A pz orbital is involved during hybridization, particularly during what? A sigma bond. Is it clear? And if they are asking with respect to pi bond, either if it is 1 pi bond, then either it can be what? A px it can be, or it can be what? A py. If there are 2 pi bonds, both are involved in what? A pi bond, that is px as well as what? A py. Is it clear, students? And now we can move to the next question. The next question is 13th one. Diagonal hybridization is another name of. It is a typical memory based question. It is the option is what? Option C, that is sp hybridization, which is nothing but what? Linear. Other name for linear, the linear type of what? Hybridization is nothing but called as what? Diagonal hybridization. Next one, the next question, that is 14th question. The two sp hybrid points in the, or what, hybrid orbitals, okay, points in the opposite direction along the z axis with the projecting lobes are of size taking positive sign as what, overlapping end, right? The two sp, so if this is one sp, right, and this is the another, where it is, this is the another sp, because they have said here 2 sp, right? So these are 2 sp, so let me write here, this is sp and this is sp orbital, this is sp and this is also sp orbital, are in opposite direction. So this is in this direction and this is in this direction along what, z axis. So therefore this is z axis and this also is z axis with the projecting lobes are of size taking positive sign as overlapping. So this is positive sign and this also is what, a positive sign. And if at all if they overlap, okay, so this will overlap here and this will overlap here, okay. Now this is overlapping here and this is overlapping here. This is this criteria what it is happening here, okay. Now we have to pick the what, correct answer here, okay. More negative and less positive, no, because here the question is with respect to positive are what, projecting, okay. So same positive and negative, this is also not possible. More positive and less negative, that is what possible. So here this is what, more positive and less negative. So the correct option is option C. Is it clear? Fine. So we'll go to the next question, that is question number 15th one. Considering the state of hybridization of carbon atoms, find out the molecule among which among the following which is linear. Linear is nothing but what, sp, and if it is sp the shape is what, linear, bond angle is what, 180 degree. If it is sp, we have already learnt there should be what, a triple bond. Triple bond means central is sigma bond, above and below that is what, a pi bond, right? So therefore in option A all are saturated. Saturated means a single bond. Single bond means 109 degree 28 minutes. So that is what, a tetrahedral in nature, right? In option B this carbon, okay, that is what, if I write here CH3 single bond CH, double bond CH, single bond CH3. Now this is sp3, right? And this is what, sp3. Why? Because it is a saturated carbon, all are what, a single bonded attached to this. Now come back to this. Now here if you see this carbon is what, sp2 hybridized. Sp2 hybridized means bond angle will be what, 120 degrees. So here it is what, 120 degrees. So absolutely we can say that there is no linearity here in this molecule. Why? Because this is sp3 which means it is a tetrahedral in nature. This is sp2 which is what, a trigonal planar. Again the same thing are what, repeated here, right? And if you see the third option, so here what I can write is that if I write is as CH3, okay, then if I write it as C triple bond C, then followed by what, CH3. If you clearly see that here the carbon is of which hybridization, sp, it means the bond angle is what, 180 degree, right? Now don't ask me that, sir, what about this carbon which is of what, sp3, and how can you say that the molecule is linear? I want to say that if this carbon is here, it is having what, a tetravalency. So one of the orbital sp3 will be in this direction, one will be in this direction, third one will be in this direction, fourth one will be in this direction, okay. And now I have to write what, orbitals of hydrogen. So this is 1, this is 2 and this is 3. Now concentrate on this here angle. So this angle is what, again linear, right? Here also it is what, a triple bond, so it is bond angle is 180 degree. Is it clear now? So therefore on this basis we can say that option C is what, the correct option, that is CH3 single bond C triple bond C single bond CH3. Is it clear, students? So remaining part we will be continuing in the next video. Thank you so much.